Hello, everyone. Welcome to this episode of Eyes on Earth. Our podcast focuses on our ever-changing planet and on the people here at ARROS and across the globe who use remote sensing to monitor and study the health of Earth. I'm your host, Steve Young. Today's guest is Dr. Crystal Schaaf, a professor of remote sensing in the School for the Environment at UMass Boston. She's also a member of the Landsat Science Team. Dr. Schaaf is here today to talk with us about albedo, which is the fraction of solar energy that the Earth's surface reflects. We humans can change albedo through such activities as deforestation and urbanization. When we alter that reflectance, it can have implications for weather, climate, and other things. Let's talk about it, Dr. Schaaf. Welcome.
Thank you.
Let's go, Dr. Schaaf, a little more in depth on what exactly albedo is.
So surface albedo is the proportion of the incoming solar radiation that strikes the Earth and gets reflected back up to space. It's pretty important because the percentage that doesn't get reflected is what drives our surface temperatures, which drives our vegetation productivity. We always want to know how much incoming solar energy is being immediately reflected back off the Earth's surface. If it's a very bright surface like sand or snow, almost all of the energy is being reflected back. But if it's something dark, moist soil, vegetation, water, it's going to absorb a lot of that energy, thus changing the temperature of that surface cover. And that's also absorbed by vegetation so that they can photosynthesize and suck in carbon dioxide.
Well, then explain how the energy balance works on Earth and the value of albedo in studying that balance.
Well, again, it can change very greatly. It can move from only 20% of the radiation being reflected from a dark jungle, for instance, to almost 80 or 90% of the energy being reflected over the Sahara or over bright white snow-covered surfaces like Greenland. So when you're trying to model the entire energy balance of the globe or even regionally, you want to try to get those proportions correctly because you want to be able to figure out how that energy is changing temperatures, changing the biochemistry. The incoming solar radiation is what drives the whole system. So you want to make sure you understand how much is being reflected and how much is being absorbed by the Earth.
Well, you have a long history as a leading remote sensing expert in the measurement of albedo. How exactly did you get onto this particular topic as a research focus?
Well, I was fortunate enough to work under Dr. Alan Strahler, who's now an emeritus professor at Boston University. And so he was actually the one that was working on albedo, got the initial grants to work on it from the MODIS and MIRROS satellites, and I was fortunate enough to work under him as first a PhD student and then as a researcher.
Well, then once you got into it, you got into, obviously, the field of albedo. Tell us a little bit about how changes in seasons or just disturbances on the landscape change albedo over time and space.
Well, the biggest change, of course, is just snow cover and changes within the snow itself. Even Greenland that's permanently snow covered, there's a lot of changes on whether it's windswept or whether it's fresh snow or whether it's melted a little bit and icy. That can have changes in albedo. But of course, over more temperate latitudes, we're constantly changing our albedo when we'll have a small snowstorm that lasts for a couple of days. The ground will suddenly go from being quite dark. Here in New England, it would be dark, bare limbs, bare trees, some conifer forests, and then snow comes and the whole landscape becomes bright and white and very highly reflective.
And what's the value in understanding that information? Why is it important?
It's whenever you're trying to model weather, the geochemistry of the surface, how productive the plants are being. You want to get these proportions of the solar radiation. It's driving the whole system. So if you haven't done a good job of figuring out how that's changing in both the short term and the long term, then you're not doing a good job of modeling that whole system.
So you mentioned weather. Meteorologists use this kind of information, or
yes,
who else uses it?
It's not just the climate modelers, but the regular numerical weather prediction folks use albedo information as an essential climate variable into their models as well. And if you're doing some forecasting for very local areas, then you need to know what that surface albedo is as well.
Why? I mean, why do you need to know that?
Because if you haven't got that right, then you're not handling the temperature gradients from the surface and the atmosphere. You're not handling that connection between the land surface and the air, and differences between those can change. Wind patterns can change fog. It governs the mixing of the cold land with a warmer atmospheric mass. We recently had quite bad fog in the early morning, fog hovering right over cold land surface because we had a warm air mass come in, and then that gradient between cold and warm triggered a bunch of fog. So if you're trying to predict what the weather's going to be, you need to know how those gradients are working and just how to feed them into the models so that you get a really realistic sense of what's going on between the surface and the atmosphere.
Why is Landsat a good tool for looking at albedo and how albedo changes over time?
So Landsat is useful in that it is a 30-meter instrument. It's a nadir instrument. It's facing straight down to the surface of the Earth, and all that's nice, but albedo is actually a hemispherical quantity, and so we need to know how the radiation is being reflected, not just straight back up in a nadir sense, but in a sort of hemispherical sense, and we figure that out by having multi-angular characteristics. Landsat's wonderful in its resolution, its quality, its nadir capabilities, but it's less useful in giving us that multi-angular effect. We actually have to borrow some information from other satellites that have more of an angular hemispherical quantity to them to make an albedo product. So when we make a Landsat product, we actually borrow that hemispherical sense from the coarser MODIS or VIIRS instruments.
But when you mention things like the 30-meter resolution, I'm guessing that allows you to get, as opposed to an average over a big part of the landscape, you maybe can get at some of the variability better in smaller areas?
That's right. It gives us more of a local feel for what's going on with the variability. And you can think about this particularly important in the spring and the fall when we may have some remnant snow under trees. We may have melting going on, so some areas are getting clear, some areas are still bright. So that variability can change at a 30-meter resolution that we really can't see at the coarser satellites that are more 500 meters or a kilometer. The variation is happening within that, and that can have quite a bit of change if you're trying to figure out what the hydrology is, what the snow melt patterns are, what the changes in temperatures might be, what areas might be now exposed to the sun and the vegetation may start to wake up, things like that.
You talked about like fog and how albedo would be useful in maybe a weather forecasting sense for fog. You also mentioned wind changes. I mean, do you have some...
The gradient between two temperatures is what drives wind. So if you've got sharp gradients, then that's going to affect your wind patterns and to some extent your speed. So all that gets plugged into a typical local weather forecasting model.
You've talked before, I think you've mentioned like if you've got a big forest somewhere and right next to it is open fields, snow-covered fields. I mean, albedo can be very different.
Being absorbed by a dark conifer forest, and then there's a lot of energy being reflected by the bright white open snow-covered open fields, and so that causes a gradient as well. In both temperature and energy being absorbed, that's affecting the atmosphere right above it.
Is albedo important in monitoring vegetation growth or change?
We can use albedo. Consistency is important when you're trying to capture little bits of vegetation change, so you can monitor albedo over time over a location. One of the ways we do that is we'll monitor albedo over a burn scar. There's been a burn, think up in a boreal forest, think up in Alaska. There's been a burn scar caused by a very bad fire. For a number of years, that area will be bright white, open, snow-covered during the winter, spring, and fall. But then slowly the vegetation will start to come back and it'll start to transition.
And so when it transitions, that changes the reflectance.
Right, absolutely. The forest comes back, and it may be a slightly different species at first, but it'll slowly revert to the surrounding landscape. But for those years that it's trying to repair, it's going to have a different albedo than the surrounding forest.
I think I've heard you talk before about like pest disturbances. I mean, albedo plays a role in those too, right?
Yeah, absolutely. Places where we're right now in New England, we're being very badly affected by the hemlock woolly adelgid. It's killing all of our hemlock forests in the eastern half of the U.S. Those are foundational species. They're very large trees when they are growing in the wild and growing naturally, and as we lose those, as they die because of this invasive pest, that's leaving wide open spaces. For a while it's a standing trunk with no foliage on it, but that eventually falls, and so there's these new openings in the forest that used to be covered by hemlock that's now going through succession, and some understory plants, some deciduous plants. Here in New England it's black birch will fill in and be a deciduous tree for a while, and then maybe some other conifer will take its place somewhere down the line, but we're in the process of losing that whole ecosystem, which is quite sad.
You mentioned fires in Alaska. We've talked about a little bit about how changes in albedo at local scales can affect wind. There's been a lot of coverage on the wildfires out in California. Does albedo play any kind of role in events like that?
Well, again, we'll be monitoring the albedo for the after effects, how long these areas take to recover. The West has been impacted by some invasive pests itself. In some areas, there's a lot of standing dead, which serves as fuel. So again, if you're trying to model it, you are recognizing that the albedo is very different. Right after a big fire, everything may be black and dark just because of the soot and the leftover cinders, but then slowly the plants will change. The first snow, if it's an area that's received snow, the first snow, it'll be bright white. Maybe there's a few stumps standing around, but there's not a lot of canopy cover. As understory plants creep into that burned area, they'll change the albedo of that local area, that landscape. As a monitoring recovery, we certainly are using it. Beforehand, we may be using it if there is some sort of a problem with invasive pests or understory growing up. That's one of the problems with wildfires out west. As people move into those areas, faster, quicker fires that kind of burned out the understory have been suppressed, and that provides some more understory fuel for fires. So certainly we can monitor those kinds of land cover changes with surface reflectance and albedo.
That's fascinating. Well, Dr. Schaaf, let's talk a little bit about Landsat Next, which is being developed right now. What recommendations do you offer that allow future generations of Landsat to improve the measurement and understanding of albedo on Earth's energy balance?
Well, we're very interested in consistency. On one hand, we want the albedo measurements to continue on as they have, so that right now we have this fabulous multi-decadal record from Landsat, and we want that to continue. We don't want to try something so different that we don't have that consistency in spectral channels and in the spatial resolution, in the consistency of the Landsat product. At the same time, we'd all love having availability of something a little higher resolution. A lot of users are very interested in moving to 10 meters or 20 meters or something that gives them a little bit tighter spatial measurement on the ground. So that's certainly something that's considered. For some communities, I'm thinking ocean communities, there's interest in vegetation health communities, there's interest in adding a few little spectral channels that have shown sensitivity to that. All that is of use to me, a better specification at a higher resolution. I'd be happy to produce albedos at a little bit higher resolution as well. Those are all things that we're considering on the Landsat 9 team as we look at all the users and researchers and try to come up with future satellites that are going to both preserve the consistency and provide more information.
We've been talking to Dr. Crystal Schaaf, a professor of remote sensing at UMass Boston. Thanks for joining us, Dr. Schaaf.
Thank you. It was fun to talk about Landsat and albedo and all those good things.
We hope you come back for the next episode of Eyes on Earth. This podcast is a product of the U.S. Geological Survey, Department of the Interior. Thanks for joining us.